Hello, my name is Hunter LaCroix, and I'm a graduate student at Western Illinois University, studying mathematics with the Department of Mathematics and Philosophy. And this presentation is going to be about the research I did with Dr. D. Ekanaika from the math department. This is about alternative stable states arising from density dependence in the SIR model. The outline is going to be, I'm going to build a background and explain what alternative stable states are, what the Allee effect is and how it relates to each other, the Allee effect and alternative stable states. Then I will explain the SIR model and explain what our generalized version of the SIR model allows us to do, with some examples in the end as well. All right, so alternative stable states. In ecology, alternative stable states refers to the occurrence of multiple stable states of an ecosystem. So we can kind of think for a certain set amount of parameters. So for like mean temperature and latitude, we're kind of keeping track of some variable, which is the tree coverage. And the idea is that these systems can transition between states due to a change in the parameters or a perturbation of a variable. So if we temporarily change the parameters, let's say there's a summer with a really high mean temperature, that might cause the tree coverage to lower due to fires and stuff, for example, which might cause us to go to a less forested, deserted state. And that's another stable state. The other one is that there's a perturbation. So like some kind of catastrophic event, like a meteorite just knocks out a lot of the trees. And that's another way that they can shift down to sort of this other stable state being a deserted state. This is useful for study as they can predict and model catastrophic ecosystem shifts, but the applicability may currently be limited. And let's talk about the Allee effect. The Allee effect is when traits of the population may cause a positive correlation between population growth and population density at low densities. So for example, higher population means that there's a more likely chance that mates will locate each other, which raises the birth rate. And the opposite is also true. And a raise in the birth rate will also raise the growth in population. So right there, there's a correlation between population growth and population density. This only occurs at lower densities. Otherwise, there's this kind of a runaway effect. And there's some other social interactions that can cause this as well, but we'll dive into that later. So the Allee effect can be modeled by a differential equation model. So right here, we have a differential equation. On our x-axis, we have the population, which we use n for. And on the y-axis, we have dn over dt. That means the change in the population. So let's say we start at 50 population. Now, our population, the change in population through time is positive. So this is going to go rightward. And actually, we're going to end up landing at this point right here. We're going to go all the way rightward. Let's say we start at 90. Now we have that the rate of change of the population over time is negative. So as we go through time, we're going to decrease up until we also get to this point. So for slight nudges around this point, we're going to come back to it. So we call this point stable or a stable equilibrium. Now, if we start at n equals 10 for our population, it's going to be negative as well. So we're going to go to the left, and then 0 is our stable point right there. And the idea is that these are two alternating stable states. And we call basins of attraction all the starting points that will go to a certain point. So this is the basin of attraction of 0 right here in the yellow. And this is the basin of attraction for this n equals 80 in the green right here. And if there's a basin of attraction towards 0, like what we have in the yellow, we have the strong Allee effect. And we're really looking at the strong Allee effect in this project. Our model is a system of differential equations that can exhibit the Allee effect. And a system is admittedly a bit more complicated. And we can sort of plot it with this right here. This is called a compartmental diagram. So our model is a system of differential equations where our variables are the population of susceptible, infected, and removed individuals. Susceptible peoples are in peoples who can be infected by some disease. The infected are the ones that were infected by a disease, and the removed are ones that are immune due to vaccination or some other factor. And the way that we read this compartmental diagram, I'm not going to dive too much into detail, is that these arrows sort of tell us the rate of change of certain of these variables. So for example, the amount of infected people and the amount of people who can be infected, there's going to be a correlation between how many there are and the rate of new infections. And that's actually what this arrow over here is kind of telling us. It's saying, okay, beta, which is just some rate parameter, and S times I is going to be our change in I over time. And it's going to go away from the individual. So it's kind of subtracted from the susceptible population, and then we gain more in the infected population. The other interesting things here is that we have births that start out susceptible. And then there's also a rate of death for each of them, with there being a slightly higher rate of death for the infected, if we'd like. Okay, so previous work on epidemiological models with alternative stable states. Kang and Chavez provided a disease model with the Ali effect and dispersion. Friedman and Yukabu, they obtained conditions that guaranteed host population persistence or extinction with the Ali effect over time, whether or not they survive or not. Then Kaneyake and Kaneyake studied a seasonal SIR metapopulation model with the Ali effect to investigate the sylvatic plague within prairie dog colonies. What is the point of this model? Well, the common model used for the Ali effect has a rather particular unrealistic curve for birth rate and crowding death rate. And I'm actually going to move on to the next slide because I can explain it really well here. Our per capita birth rate function, which is B of N, we see is linear, and our per capita death rate function, D of N, as you see, is quadratic. But this rarely happens in nature. We might get some data points for our birth rate that's like this. And one might conjecture that we might have more accurate results if instead we just interpolate through this and then define this as our curve for the per capita birth rate. Similarly, we can use qualitative data. So let's say that as a population gets lower and lower, there's an increased rate of death because they can't collectively evade prey anymore. This has been recorded in, I think, fish populations and stuff, for example. Then one might conjecture that as we go down, our per capita death rate is going to increase like that. And so the idea behind our model is that it's actually possible to use these curves instead of just the normal curves that the Ali, that the regular model for the Ali effect uses. And that really changes things for us, actually. All right, some other things about results with our model. The population is going to just be the susceptible plus the infected plus the removed. And the change in the population is given by this equation, but I actually plotted a couple of cases of this equation. In the blue, we have what happens whenever the infected death rate is equal to the regular death rate. And then in the orange, we have what happens when the infected death rate is higher than it is for just a regular individual. And as we see for the orange, the basin of attraction in yellow here is greater than the basin of attraction for the regular case. And also the stable state, the one that's non-trivial or not zero, is going to be a slightly lower population in the end. So that's just kind of an interesting result that we get from this. The other one is that, okay, let's think about these non-zero stable states. There's actually multiple cases that we can have for these. And the idea is that we can go back and look at the basic reproduction number, which that's the expected number of infections that will spread from one case. For example, for COVID-19, R naught, which is our number, was approximately 3.32. So for every one person infected by COVID-19, 3 more people were expected to get infected by them. And with our model, we were actually able to get an expression for the basic reproduction number. And based on its value, we get 2 different stable states. One where it's endemic, whenever R naught is greater than 1, that means it's going to, the infection is going to spread faster than it declines. And whenever R naught is less than 1, we have a disease-free case. And we can see that our basic reproduction number, it's going to be proportional to our beta, which was that kind of scaling factor that we had on the amount of new infected individuals. And we could also see, for example, V is our vaccination rate, and it's in the denominator here. So as we increase V, our basic reproduction number lowers. So hypothetically, we could get the case where we can increase vaccination so much that we instead go to the disease-free case. All right. And here's some examples of that former one, the beta being increased. It's kind of doubling each time here. On our first case right here, we just have that the infection sort of dies out over time. The infected population is in orange. Over here, we have the endemic case. We finally increased beta so much that R naught's greater than 1. And here, increasing beta is also going to increase our infected population, which if we look at our equation from earlier, that's what kind of causes there to be this decrease, or sorry, this larger basin of attraction for our trivial case. So in this one, the basin of attraction gets so large that with our initial conditions, the population just collapses from this disease. So we see 3 different stable states just for this, just for varying our beta here. All right, now let's look at some examples using our model, but with more interesting curves. Consider a population of flower beetles in a controlled environment of flower. So there's an abundance of resource, so we consider our death rates to be constant, or our per capita death rates to be constant. And then to follow experimental results, we can set our birth rate to this curve right here. It's kind of a weird looking curve, but one could think of somewhere where this might be true. The birth rate increases at first due to increased fertility from increased copulation, but after a point, it goes down from euphagy, which means the eating of one's own egg, because we're in a small controlled environment. So it's going to be hard to like not accidentally eat eggs. And that's going to cause, as we increase, a slight lower rate in the per capita increase in the population or of the birth rate here. And something else is we can add stochasticity to our model using what are called etostochastic differential equations. And essentially what this does is for some jump in time, we have a slightly different value for like how many new infected people get, or how many more people get infected, or how many people get born, for example. And it's actually going to be normally distributed, so it kind of acts nice. And here are a couple of models using a deterministic one without this randomness or stochasticity, and then one with the stochasticity. Our one above has the disease-free equilibrium. The infection dies out over time. The one at the bottom, the infection is endemic and it stays there. And even though these are random, we can see that they also kind of act in a similar way. But it is also completely up to chance. We could have by chance that our population dies out, or that the infection just dies out really quickly and then we never actually get a disease. All right. So another example is that a paper by Kaneyake gives deer birth rate in this form. So we kind of have that it increases like this and then just tapers out to a point. And if we choose a linear crowding per capita death rate, we can get alternate stable states. And furthermore, the last thing we added to our paper is that we sort of added this sigma of t, which could represent temporal variations and allocation of resources. So the idea is that, okay, alpha 1 and alpha 2, those are just constants that could be something that has to do with the deer population or the environment they're in. So it could be USDA hardiness number. And M star is the critical weight. That's the weight of the deer where they can't give birth anymore. And then M is the average weight of deer. And the idea is that as we increase the average rate, the birth rate increases. This is the per capita birth rate once again. And depending on certain resource values, that's also going to change what the birth rate actually is. And we can change them over time. Our sigma is a function of time. So we're going to make this temporally dependent by making our birth rate equal to 0 when not in the spring. So we're going to try to divide our times by seasons. We have a third of the year is spring, a third is summer and fall, and then a third is winter. And actually during winter, we're going to increase our crowding death rate constant. And so what we get is a model that looks like this. As you see, for the first third of each year, we have that the population sort of increases, and in the latter parts of the year, they start decreasing because there's not births being added. And we see that the infected population kind of follows that. And the interesting thing is that just by chance, this is kind of the endemic case here, but just by chance, the infected population dies out. That's kind of what's interesting about these stochastic simulations. And then finally, something I did is across this axis right here, I varied the mean body weight. And then across over here, I varied the scale from the infected death rate to the regular death rate. And I plotted the probability of population collapse. So I ran like 1,000 simulations and found the probability that they would collapse. And we get this interesting curve. We can see that as mean body weight increases, it decreases. And as our scale increases, it also increases quite dramatically, actually. So that's the presentation I have. The big important point is the fact that we can change our curves for the birth rate and per capita death rate. And here are my sources. All right, thank you.